Okay, good afternoon, everybody. Apologize for the last second delays, just having version issues and connectivity issues, and dumb me has my mute button on, and why isn't my audio working, etc. like that. So this is what you get when you're 57. All right, so anyway, so thank you all for coming. Hope you had a good holidays. Back to work from January or so. My name is Jim O'Donnell. There's my contact information on the screen there. We're going to talk about cold climate airside heat pumps today. In the past year or year and a half, I've done a few presentations about airside heat pumps. So some of the information is a repeat, but I just wanted to emphasize the differences with the cold climate and just the direction that the industry is taking. So just a couple of housekeeping, just apologize. Some people asked for Chipotle gift cards, and we had issues with their web server, so we're trying to get that figured out. We will complete them. We're going to try to keep the attendees muted. We'll monitor the questions. We'll try to leave them until the end of the presentation. If there is something pressing, we will interrupt and answer that. And then just myself want to thank you to Gianna Salvatore and Ricaditis for helping me out with this. As all these presentations, we do have a PDH available, and there is a survey at the end with 9 questions or so. If you could fill it out, it would be greatly appreciated. It helps us with the topics that we have covered, as well as upcoming topics and questions, etc. like that. All right, so let's get started. 4 things going to cover today is just the definition, or just introducing what is a cold climate heat pump. The majority of the presentation, I'm going to try to focus on applications of using this cold climate airside heat pump. Just a quick comparison, a couple slides, just understanding the differences of an airside versus a waterside heat pump. And then, as always, what's new at HCNI, as well as cold climate heat pumps are tailored to Aeon's packaged rooftop units. All right. So going quickly through the review, just airside heat pumps as a rooftop unit. There's all your items that make it a nice packaged and pre-engineered rooftop unit. Today we're going to focus on the DX system, where we're going to provide heating, as well as the supplemental heating that is required in addition to the airside heat pump performance that you are achieving. Quick recap, or just understanding of our heat pump system. Here's a traditional cooling system where we're taking the energy or the heat from the indoor coil, running it through our refrigeration system, and then expelling it outdoors. There's some of the components that are included inside your refrigeration system. The heat pump is taking the same system and just reversing the mode, where they're transferring the heat from the cold outside air into your refrigeration system and then delivering it to the indoors. One thing that we have going in our favor with the airside heat pump and the heating mode is that the compressor is generating energy or adding heat into our refrigeration system that we can utilize for our heating applications. What has been added to a airside heat pump, once again, a repeat slide, suction accumulator, those specialties, etc. like that. The controls, once again, recap, just a freeze stat to keep track of the refrigeration temperature, and then we've added the sequence of operation defrost control. Just try to emphasize that this is a small dollar add, and now this is becoming more of a standardized option where manufacturers are including this, right from the get-go. Benefits of airside heat pumps. Everybody's aware of the trend of reducing fossil fuels, or eliminating fossil fuels, and changing to electric. Just the picture there is my gas burner, which I really love that they want to get rid of. No comment on that. And then just some headlines from last summer that I was too lazy to change, but probably since then there's been 50 or 100 other articles regarding electrification or decarbonization. And then just an interesting thing, that the Department of Energy has issued a cold climate heat pump challenge. This is for residential products, but they're working with the major manufacturers to try to implement cold climate heat pumps in residential systems. Benefits of airside heat pumps, as you're well aware of, energy savings with high efficiency. Heat pumps, the heating efficiency is evaluated by a term called coefficient of performance. Like any efficiency, it's an output over input. In this case, we're heating output over energy. Just an airside heat pump has a coefficient of performance that's higher than electric and gas heat. Just put it in parentheses because approximately I've seen values as low as 1 and then up to a little bit above 4.0. Just doing a simple payback analysis using an old Excel spreadsheet that I've had for a few years. Using these inputs, 15-ton unit, this utility cost, office hours where it's 12 days, 12 hours for the weekdays and half a day on Saturday. Instead of working at home, you'll go into the office, chuckle, chuckle. And then using only the bin temperatures between 45 and 25, which comes out to about 1,100 hours per year. Roughly, the payback is 5 to 8 years if you implement the airside heat pump versus the gas heating. There is additional cost, but you are saving energy. And then just an alternate analysis is, of course, as you ramp up your operating hours, your payback period is reduced. Other benefits of the airside heat pumps: when it's mild out, when the temperatures are, say, 35 to 50, the airside heat pump will work better than the gas heat. Just here's a design where designing for 0 degrees, your mixed air temperature and your leaving air temperature, you've got about a 40-degree delta T. That's at your design conditions that are 0 or 10 degrees. What happens if you look on the chart is as you get warmer, so say 47 or 42, your mixed air temperatures are in the mid-60s. The problem you have, or the issue you have to be concerned about, is just when it's that warm out, you don't need much heating. Your gas heat still has its 40-degree delta T. And then just what's going to happen at these milder temperatures is your gas heat is going to try to modulate down. It might be too low for the minimum stage, and then you're going to get cycling on and off. And then just the airside heat pump, because we're using modulating compressors, whether they're digital scroll or VFDs, you'll have much better capacity control. Limitations of airside heat pumps: number one is the heating capacity in the wintertime. Heating equipment is rated at 47 and 70 degrees ambient. Just as your ambient temperature drops, your heating output drops. Everybody's familiar with this if you've worked with VRF systems. Just for our rooftop unit, here's your output at 47 degrees and 70 degrees ambient. I also just put in what the delta T was at those two ambient temperatures for our system, for our rooftop unit there. So in this case, we had a reduction of approximately 40%. Other limitations of the airside heat pumps is you have a safety called defrost mode that occurs in the wintertime. Here's a P and H or enthalpy diagram that shows your refrigeration circuit. You have to just remember that we've gone to the reverse cycle. So our outdoor unit is now the evaporator. We're taking heat from the outdoors, implementing or entering it, importing it into our refrigeration system, and then we're expelling it indoors. This happens during the wintertime. And what will happen when the ambient degree temperature is 40 degrees or lower is that a refrigerant temperature / pressures are going to drop. Eventually what will happen is our temperatures of refrigerant gets too low to operate in heating, and boom, we'll have to activate our defrost mode. So what is defrost mode? We're basically trying to warm up the refrigerant. So the first thing that we'll do is turn off the airside heat pump and heating operation. We'll reverse the refrigerant circuit, so we're effectively cooling. We'll run the compressor at 100%, and then we'll heat up the refrigerant with the heat in the airstream. Just note that the airside heat pump is not in heating mode during these winter operation times. We'll turn on the supplemental heat to satisfy the space temperature. That will also help up warm the refrigerant. And then the other thing that will happen is that defrost mode that I talked about in a in the sequence of operation, you're basically going to turn on a timer, and you have to, typically it's set for 10 minutes before the unit can switch back to heating. All right, so what is a cold climate heat pump? Essentially what we're doing is we have that same Airside heat pump, but we're going to operate at lower ambient temperatures and produce more heat. So our ambients are going from the traditional 47 to 17 down to 0, down to -20. Currently, the industry seems to be at about 0 degrees ambient for their testing and operation. They are planning to go lower in the future. And then what are the 4 things that have been done? So the first one is that the equipment manufacturers and the compressor manufacturers are doing a better job with testing for this cold climate heat pump. It's critical to match the performance of the indoor coil and the outdoor coil in heating as well as cooling mode. But the biggest change that's occurred is changing the compressor. Once again, they're sort of borrowing from the VRF industry, where they're taking a VFD compressor and they're overspeeding it from 60 hertz up to 90 to 100. As everybody knows, that produces additional heating output. And then inherent with the VFDs, et cetera, like that, they're upgrading the controls, and there's switching. That little gold picture there is a electronic expansion valve that's changed from a thermal. And everybody knows a variable speed compressor is great for accurate capacity control, as that traditional graph shows. The third thing that I tried to minimize, just making it a little bit smaller in the font, is the condensing system. This really hasn't changed that much. The condenser fan controls have already sort of been implemented for head pressure control with the VFD or /EC motor. The other thing that's happened overall is just better controls by using the VFDs, as the industry moves from electromechanical controls to DDC. In addition, there's a thing called adaptive defrost controls, where it's a little bit more accurate and it's tracking the defrost mode. If it realizes, okay, I didn't have to run for 10 minutes, the next time, I'll reduce that interval so my defrost mode is not occurring for 10 minutes. Maybe it's down to 9, and then down to 8, down to 7, et cetera, like this. And then just to emphasize once again that the less defrost mode that we have, the better it is for a system, because we have more heating output. All right, so that was just a quick review. Next, going to do some juggling with the application of cold climate airside heat pumps. Just you guys as designers and installers have a lot of things to consider back and forth when selecting your cold climate airside heat pump systems. The first one I wanted to compare was just the cooling output. I took 3 instances where you have a cooling only rooftop unit and a traditional airside heat pump, and then the cold climate airside heat pump. There's my unit that I used. Just as a side note, what I did for this presentation is, rather than creating new units and stuff like that, I took equipment from jobs that I'm working on that have airside heat pumps, and just tried to not play around, but just run through the different numbers and scenarios to try to explain or just show what you people are faced with. So using a cooling ending air temperature for those 3 systems, the first one is a cooling only versus an airside heat pump. These are both using a digital scroll compressor. You can see the cooling, this is a 25-ton unit, so it's not like you're getting a 30-ton capacity. You're getting 25.5, 24.5, et cetera, like that. But what happens in this case is that the airside heat pump has a little bit less cooling capacity. I attribute this to the airside heat pump is adding those specialties that I showed you before. Now comparing an airside heat pump with the digital scroll to the cold climate airside heat pump with the VFD. In this case, the airside heat pump with the VFD had a little bit lower cooling, leaving air temperature, and hence a little bit more capacity. For this situation, I attributed that to the airside heat pump went with a 6-row coil versus the the matching of the digital scroll was a 4-row coil. Once again, just on the cooling, you have a lot of different options for rows and reheat, et cetera, like this, that will slightly change your performance. Now, heating. Most of this presentation is going to look at the heating. If you compare an airside heat pump to a cold climate airside heat pump with that unit there, the airside heat pump with the digital scroll compressor at those two ambient temperatures has that much heating output. If I have a cold climate airside heat pump where essentially I've changed to a VFD, what has happened is at those same ambient temperatures, my heating capacity is a little bit lower. What I'm attributing this to is that the heating output, whether you're a digital scroll or a VFD, is about the same, because the VFD is not overspeeding at these milder ambient temperatures. But where the difference occurs is when you drop your ambient temperature. So in this situation, the airside heat pump was not able to operate at 0 degrees, hence it's producing zero heating, whereas the cold climate airside heat pump at 0 degrees produced that much MBH, which turned out to a 22-degree delta T. Now, obviously, the VFD and the cold climate heat pump cost more, but versus the digital scroll. But one of the benefits that you're well aware of, the efficiency of a VFD versus a digital scroll compressor. That's the part load comparison just on a couple jobs that I looked at, the COP for heating. And then once again, the VFD is more accurate for operation and control when compared to a digital scroll compressor. Now, when you select an airside heat pump, one of the output sheets that you can or will receive is basically a chart going from left to right. This has the intermediate temperatures and performance instead of just at your design conditions. So starting from the left, you have your outside ambient temperatures in 5-degree increments. You have your associated mixed air temperature. That mixed air temperature obviously is mixing your return air and outside air. And then the next column going from left to right is your leaving air conditions. This is with the airside heat pump operating. As you can see from the mixed air to leaving air, we have a temperature rise. The next two columns are your heat pump capacity, and then another item called integrated heat pump capacity that I'll talk about in a second. And then the last item way over on the left is the COP that, once again, to remind you, is our efficiency of our system, how much energy, how much heat you're producing versus your energy input. So I want to highlight the heat pump integrated capacity. This is a little bit different than what you traditionally have seen. If you look at starting around 42 or 37 degrees for most of these charts, you notice that the heat pump capacity versus the integrated heating is a little bit lower than the heat pump capacity. So what it is the integrated heat pump capacity is they're partially reducing the heating capacity due to defrost mode, and they're subsequently adjusting our leaving air temperature lower. So if you look at the chart, once again, the integrated heat capacity is applicable from 37 degrees lower with the ambient. And then once again, that airside heat pump output leaving air temperature has been adjusted to reflect the integrated heating heat pump capacity. All right. Now the next thing, supplemented. You have the airside heat pump. Obviously, is providing heat. Do you need supplemental heating in addition to that? For the most part, probably yes. The reason why is if you look back at our chart in this situation here, as your ambient temperatures get lower at 27 or 12 degrees, your leaving air temperature on the heat pump becomes 84, 72 as it gets lower down to 63. In most cases, I would say that this leaving air temperature is too low. And then the other thing that you should consider is that at these ambient temperatures below 37 and 40 degrees, 45 degrees or so, the refrigeration defrost will occur. Just once again reminding the airside heat pump is not in heating. And then just the defrost mode is kind of hard to predict. A lot of times it depends on your entering air temps, how many run hours, et cetera, like that. So just to highlight just the need for defrost mode, There's a definition of bin temperatures that everybody should be familiar with. Just took Philadelphia as an example. So these are the ambient temp, the ambient temps, how many times it occurs a year. So if you were considering 24/7, 365 operation, approximately 26 or 25% of the yearly hours, the ambient temperature is below 37. And if you take that down to 17 degrees, you obviously have that much lower at almost 200 hours per year. And then just as a comparison, jokingly, what would an office be that nobody's in 5 days a week and half the day on Saturday? Obviously the run hours, the bin temperatures at 37 degrees and 17 degrees are lower for two reasons. One is obviously there's less hours per week. And the other thing just to realize is that, wintertime, the daytime is obviously much warmer than the nighttime. All right. So your additional heating solutions that you have available to you, first off, obviously is inside the rooftop unit. You can add supplemental heat, just highlighted electric, just because we're talking about decarbonization, et cetera, like that. So we're going to focus on our electric heat. And then just want to highlight that this auxiliary or supplemental heat is in the reheat position. So our unit will be set up to use the Airside heat pump for first stage of heating and the additional supplemental heat as a second stage, which once again plays right into our energy efficiency improvements. Airside heat pump is going to run for the majority of hours. Your additional heat might never come on or come on for a very short number of hours per year. The next two items to consider is similar to the VRF industry, where we can oversize our rooftop. We're going to design for the heating load as well as instead of cooling load. For our rooftop unit, it's very easy to add an energy recovery device. And then like any system, you can add external heating systems where it's baseboard for barrier, draft barrier, duct heaters, VAV boxes and stuff. And then once again, similar to the VRF industry, you're very familiar with oversizing, fan coil units, et cetera, like that. You're sizing them based on the heating load in the space versus the cooling, more critical versus the cooling, and then once again, adding external heating to your system. So before we go into those four different solutions, just once again want to point out, what's your application? What percentage of outside air do you have? Obviously, the higher percentage you have, the more heating you're going to need. Are you a constant volume VAV or single zone VAV system? What's your leaving air temperature? Obviously, a VAV system is traditionally in the 55-degree range. Constant volume, what's traditionally used is 95. If you have a DOAS unit, DOAS sort of implies that it's 100% or very high percentage of outside air. What can make a difference with that is your supply air discharge. Are you dumping it directly into the space from a ceiling diffuser, or are you dumping it into the back of a mixing box on like a terminal unit, such as a fan coil water source heat pump? Obviously, if you're dumping it directly into the space, it's much more critical that temperature be maintained at a constant or acceptable temperature. Other things just off the top of my head to consider: is this a new or replacement job? We'll talk about looking at the existing electrical service, how many operating hours, if you have something that's not going to really ever work in the dead of winter, maybe you wouldn't have to be so critical of the outside air temperature. Your design temperature. And then also too, the main thing is heating. Is it gas or electric or using something else? And then, as I said, what's an acceptable leaving air temperature is a big criteria, whether you have those type of sequence of operations. And then the other thing you want to look at is, are we going to take credit for the Airside heat pump operating? Or are we going to ignore that and use a lower leaving air temperature where the unit is not in heating mode? All right, so looking at solution number one with the rooftop unit, we're going to take a rooftop unit, make it a cold climate one with electric heat. Just from the computer program, here's your outputs at your different ambient temperatures. Those same ambient temperatures, this is what your mixed air temperatures are. This, to note, this is before. This is before you're adding the heat of your airside heat pump. And then your leaving air temperature from the airside heat pump has those numbers there. So just to highlight, the bottom ones from 0 and 54 as well as 65. So if we're going to design our heating, our supplemental heating system for using a 95-degree ambient temp, if we use the capacity or leaving air temperature where the after the airside heat pump, we would come to an approximate electric heater of 50 kW. Now, what happens if we use the lower temperature of 54.6? Note that this is the airside heat pump is operating. This could be considered in defrost mode. You would have a choice of, say, a 60-degree electric heater. You would have this leaving air temperature, maybe 89 is okay versus 95. That's your electrical service. The next option you could look at is to upsize that for an 80 kW. There would be your leaving air temperature, obviously warmer versus a 60. And then your electrical service obviously gets larger. So traditionally on a unit, a rooftop unit with electric heat, you have 3, 4, 6, in this case, 6 different heating options. Traditionally what happens is the electric heat is sort of undersized. I think the main reason for that is if you look at the MCA, there's not much of a cost difference between the electric heaters, but there could be, down the road, a lot of, associated costs with the higher electrical service. Now, checking your electrical service, just realize that with an electric heat in the rooftop unit, you have 2 electrical circuits. You have your refrigeration circuit with your compressors, also your condenser fans. You'll have 3 control/power options available. So taking our same unit that we just looked at, we're going to use a 60 kW electric heater. Option A is called simultaneously operation. In this situation, the electric heat and the refrigerant can both operate at the same time. Usually, this results in your largest electrical service. Just realize that you're going to have to look at or consider defrost mode with the implications of that. In this situation, your MCA was this value. The next one is called MCA limited. This is where the electric heater amp draw can't exceed the MCA. This has the same, and I'll just say that traditionally this is not an option or looked at. This is only occurs when you have very large rooftop units or electric heaters, or if you have 208 volt power versus 460. Obviously, 208 results in larger amp draws because of the lower voltage. Option C with our electrical service is you can have it where it's either or operation. In this situation, only the refrigeration circuit or only electric heat could run. They cannot run both at the same time. Usually this has a smaller electrical service. What typically happens is you lock out the airside heat pump to not operate below, say, 50 to 35 degrees. You have to just realize that if that airside heat pump did go into defrost, the refrigeration circuit is running, and our electrical service is only sized for either the refrigeration or electric heat to run. So basically the supplemental heat can't run. As I said, comparing the electrical service is smaller. So what the 2 choices that are most looked at is option A, simultaneously, or option C, on off. There's a quick just comparison. Obviously the simultaneously, where you're running the airside heat pump, you're getting a greater energy savings. And then just with these 2 options here, just a thing to consider with the electrical service, just to divert a little bit, or go on a sidebar, is looking at a new versus replacement job. So this is this is sort of a repeat from last summer, where we're replacing the existing unit that has gas heat with electric. So here is our 15-ton unit that we just looked at. Gas heat has that MCA, MLCP. If we go to an airside heat pump, our amp draw goes a little bit higher because of those refrigeration specialties that were added to make the unit slightly more inefficient. But where the really big change occurs is when you add that electric heat to the airside heat pump. In this case, simultaneously operation is with both units both electrical service running, which is what's selected most of the time. And then just as a comparison, back last summer, I found a slide where I did the same similar comparison to an 8-ton unit with 208 volt 3-phase. You can obviously see the existing electrical service is much smaller than the new one that you would be required to provide. And then also just as a sidebar, instead of the electric heat for this, the supplemental, let's look at gas. So once again, just comparing the simultaneous versus either or. Simultaneously, they both can run at the same time, so you're taking credit for the Airside heat pump. Usually the simultaneously has the lower gas service. Whether the either or means is that the Airside heat pump is not operating, and therefore you're only using the electric heat. So going to the numbers here, just the ambient temp at 0 degrees design with the Airside heat pump, your leaving air temperature, I'm sorry, your entering air temperature of 65. If you're looking at a leaving air temperature of 195, that would be your gas input. And then if you took the lower leaving air temperature, your gas input would be higher. Typically what happens in gas heaters is you have 3 different sizes available, 3, maybe up to 4. And traditionally what we've seen happen is that the gas heat, there's such a small price difference between the sizes of the burners that traditionally we recommend, or just we see engineers or units that we select with a larger gas heater versus maybe what you can maybe get away with. All right, going to option number 2, where we're going to oversize the rooftop unit. We're going to look at a 15-ton versus a 20. Here's our heating output at those different ambient temperatures of a 15-ton unit. If we take that same conditions and switch it to a 20-ton, you can see our heating output has increased. At the 17-degree ambient temp, we've basically increased the capacity by 50%. And then at 0 degrees, we've added an additional 15 degrees of temperature rise. So now is that 20-ton unit, is the cooling oversized? What about our part load capacity? Just because we have a VFD or a digital scroll compressor, they can modulate to turn down. You do have to obviously, as always, at any system, fan, heating, cooling, you have to look at your minimum loads versus what the unit can turn down to. And then in this case here, a 15-ton unit had that leaving air temperature, and a 20-ton unit had, obviously a lower leaving air temperature. I put a check mark just because the 52-degree temperature is definitely acceptable. It's not like you're going from 52 down to 45 or 42 something, where you have to be worried about you're operating at the edge of the equipment's operating envelope. Option number 3 is to add an energy recovery wheel. Everybody's familiar with an energy recovery wheel. We're recovering heat from the exhaust air to return air back to our 15-ton unit. These are the mixed air temperatures without an energy recovery wheel. That's your Airside heat pump at 0 degrees ambient. If we take that same 15-ton unit and add an energy recovery wheel, we're raising our mixed air temperature, you can see, significantly, 11 and 15 degrees. And then the other thing just to realize that our design conditions is that in addition to the Airside heat pump, we're adding sensible and latent heating capacity due to the wheel. What happens now in your cooling is your cooling oversize. You basically have a 15-ton refrigeration circuit with a 4-ton energy recovery unit. Looking at the leaving air temperature, instead of being in that 54-degree range, maybe we're at 52. I just looked as a comparison. Maybe you switch that to a 13-ton unit. A 13-ton unit would obviously be a tiny bit cheaper. It's probably the same cabinet size, but your leaving air temperature to me would be acceptable. And then the other thing you want to evaluate is your heating capacity. In this situation, we only had a reduction of 5% at that 0 degree design day ambient. Now the problem you have, or just everybody's aware of with energy recovery wheels, is that you do have another defrost mode. In the wintertime, you're transferring latent energy. Your return air could be too warm and or too moist. Your outside air can be too cold / too dry. Where defrost will occur is if you draw a line between your return air and outside air conditions. If that outside air crosses over to your saturation line, your moisture will condense from the air onto your surface. And then if that return air dew point temperature is lower than your freezing, you could get frosting. So here's an example of that 15-ton unit with those conditions there. Here's our return air and outside air conditions. In this situation, our exhaust air leaving the return air is below 32. So we would have the defrosting. Just as a sidebar, just to understand that if our outside air temperature starting at 17 degrees, from 17 degrees up would not have defrost. From 17 degrees ambient and below, we could have defrost conditions. Once again, a lot of it is associated in conjunction with your return air conditions. All right. So now everybody once again is familiar with defrost mode solutions. The most common one is to take that wheel and put a VFD on it and speed it or slow it down. You can also jog control, which is a high-tech term for on-off. Just note that the defrost timer is typically 2 minutes long. Another options are a bypass damper. Don't really see that in there, even though it's already included because of an economizer. And then the other item you have is to add an electric heat preheat coil. This is upstream of the energy recovery wheel. I will say that this is hardly ever done, but this is probably going to change as we switch from our rooftop units being gas heat to electric heat. That electric heat, if we put it in the preheat position, is going to accomplish a couple things. One is it's going to reduce the amount of defrost for the wheel. We're going to reduce the amount of defrost for the airside heat pump, and then we're also going to take a credit for the heating capacity, of our downstream or reheat position electric heater. All right, so going to our 15-ton unit here with our mixed air temperature. After your energy recovery wheel, before your DX coil, with your wheel is at 66. If we just look at the defrost mode without the energy recovery, we're back to 50.9. Once again, you have to consider your application as to what size, what size you're going to make your auxiliary or supplemental heater. So in this example here, just used the same conditions here. We're going to design for a leaving air temperature of 95. Your smallest heating would be at 0 degrees, where you're going to say that the defrost is not going to occur. This would be your energy recovery wheel plus your airside heat pump has a mixed air temperature of 78 degrees. The amount of heat that you need to add to go to 95 is only 102 MBH. The opposite of that would be the largest heater when you're at 0 degrees, where for some reason your two defrosts would occur at the same time. This is obviously the defrost of the energy recovery wheel plus the defrost of the airside heat pump. Back to our 50.9 degree leaving air temp. The amount of heat that's added to get to that 95 degree design is 267 MBH. And then once again, traditionally what happens is if you have a gas heater, you err on the larger size. If you have an electric heater, you typically err or shade towards the lower kW heater. All right. Next couple slides. Getting probably about 80% done here is just do a quick comparison of an airside heat pump versus water source. Water source heat pump. What we're doing obviously is in lieu of using air, we're using water or a glycol mixture. Instead of, I've just highlighted the blue circles here where we're using water instead of air. We still have the refrigeration system. We still have the air to our occupied space. In heating, as we've shown before, we're adding heat to the water, running it through a refrigeration system, and then dumping it into our space. The opposite of that is cooling, where we're removing the heat from the space, adding the heat of the compressor and the refrigerant, and then expelling the heat to our water system and then to the ambient. Traditionally, these water source heat pumps are very commonly used offices, education, multi-residence, et cetera, like that. Just a little, preview. The next webinar that I'm going to do at the beginning of March, I try to keep these about 5 or 6 weeks apart, will be just to review the basics of water source heat pumps. We'll have an invite going out for that soon with more details and information. Just a water source heat pump. So our space zone equipment is similar to before. We're in the cooling mode. We're, as just mentioned, we're removing the heat from the space and then dumping it into our water system. The opposite is happening in the heating mode. And then once again, just realize that we're adding heat and energy to our refrigeration system via the compressor. But just what is mostly changed is the water to refrigerant heat exchangers. The most common one is that picture there, where it's a coaxial, where basically it's a tube-in-tube heat exchanger. On larger sizes, they do go with a plate and plate and frame heat exchanger. Here's a traditional water source heat pump system where you have multiple zone heat pumps in gray there. You have piping all connected to get them together. You have a circulating pump. You have a boiler or a heating device as well as a fluid cooler. Once again, the boiler is adding heat to the loop. The fluid cooler or cooling tower is removing heat from the loop. Just a boiler tower, not to get into it, but obviously there's many different, geothermal and lake systems available. The thing that's nice about the water source heat pump is that the zone heat pumps have all those different types available: horizontal, vertical consoles, vertical stacks if you have a high rise, et cetera, like that. And then we are now the Climate Master Rep. Talk about that in a couple slides. And then just a quick overall comparison of your water source heat pump system versus your Airside heat pump. The Airside I considered, a rooftop unit and maybe splits, maybe VRF could be included in there. Just the advantages of the water source heat pump, just because you're using water and lower, ambient wet bulb temperatures versus dry bulb. You're traditionally more efficient. This is an Airside heat pump. You have redundancy with the multiple indoor units. And then also those indoor units have much more flexibility in terms of where they can be located and types, et cetera, like that. The disadvantages of the water source heat pump rather, is this higher first cost. Supplement heating becomes tricky. You just have to consider with a boiler, maybe you're adding at the units itself. And then just because you do have the zone, a lot of times the zone heat pumps are in the space, you have to just be more careful about the noise that is generated, especially from the compressor. Airside heat pump has the opposites. Obviously, there's lower first cost. If you have a rooftop unit, it's very easy to add supplemental heating. If it's up on the roof, you have less noise concerns. Disadvantages, once again, the opposite is less efficient. You have less options for your equipment. And then just to question the future direction of Airside heat pumps, just the overhang of for splits and VRF is the upcoming change for the eliminating or phasing down 410A with the new partially flammable refrigerants. Maybe partially flammable is not the right term to use for that. Mildly flammable is a better term. And then I put sort of in the middle maintenance, just because if there's so many different systems that you could have, versus on a water source heat pump. Traditionally, it's a little bit more maintenance if you have, water treatment or a cooling tower. If you have an open system, your loop control system, which is not really, too terribly intricate. Typically, you have more of the units, but they're simpler. A lot of times on like a job with a lot of horizontal units, say 100 or so, the owner will buy an additional one as a spare. So if something goes bad, they'll just quickly disconnect it instead of disrupting a space as they try to fix it. With the Airside heat pump, obviously you don't have the whole shebang or whole deal with water. Traditionally, you have less units, but then as I kind of showed with the differences in the controls and how much to size it and et cetera, like that. Outside air versus DOAS, VAV, typically it's more complicated. So once again, maintenance is sort of, could go in either direction as an advantage or disadvantage. Next couple slides are just what's new with HCNI, as well as the available Aeon products with cold climate heat pumps. Just the big news was towards the end of the year, HCNI merged with Gilbar Solutions out of PA. Gilbar, that's their website there, very large rep firm, started up in New York City 35 years or so ago. Just what we have locally that we're all happy about, being an engineering HVAC nerd, is we have more applied systems to sell, to work on. Before we had approximately 39, 40 vendors. Now we're up to 57, 60. Just website has remained the same. Just on the website, we do have an updated line card with the products that we do have available. Just to highlight the new products, applied products and systems that we have more custom air handler solutions. We have 3 main vendors: Nortec, TMI, and Climatecraft. Nortec does have 4 different brands under their umbrella. We can size or work on custom air handlers from 500 up to 400,000 CFM, all the different types of construction. And then the other thing that we have to, chuckle, work on, improve better is that just, we have 6 vendors, 8 vendors to choose from. Which the best one in terms of where's the job located? There's multiple construction types. This one here is a full knockdown, so we have to, focus on TMI. This one here might be a low-end custom unit, not really so intricate, so maybe that's Hunter, et cetera, like that. And then the one big thing that has changed over the years is with custom air handlers. Before, if you came to us with a selection, we had to take all the information and send it to somebody at the factory, work back and forth with them. Obviously, it was not the most judicious or the fast process. Just all these vendors have made the investment to provide, software, selection software that the salespeople, sales force can use in the field. We still have to send it up there to keep ourselves out of trouble, but it can produce much faster turnaround with, when you're looking for custom air handling units, and like everybody, time is of the essence. Other products, so we have additional custom DX, still has energy recovery units, once again with Nortec, a company called Cool Air. We have modular plants with a company called Fluid Cooling Systems. There's a picture of a mechanical room with cooling towers up above, pumps, et cetera, like that. It's prefabricated, fully integrated. All these different types are available. Being an ex-carrier person, very interested in technical systems with custom heat transfer, custom energy recovery. That picture there shows an air-cooled chiller with horizontal discharge versus the traditional vertical ones if you have space constraints. Most of the projects they work on have to do with the N-1 or is that N+1 redundancy. And then they do have chillers and all these other different types of heat rejection or heat transfer systems. Last couple slides here. Healthway is an indoor air quality company. Once again, learning more about that, but it's a high efficiency filtration as well as a disinfection system. They have portable products as well as fixed. As I mentioned before, water source heat pumps with Climate Master, who we'll talk about more in the next presentation. Another company, United Cool Air. Air and water cooled chillers, Quantec have the traditional scroll and screw ones up to 300 tons. ClimateCool is a modular company, air cooled and water cooled modules from 15 up to 85 tons. The modular units obviously offer redundancy, backup, et cetera, like that. They're available as a heat pump, heat recovery, 2-pipe, 4-pipe. There's free cooling modules for an air-cooled chiller, and then simultaneously producing heating and cooling. Next one, once again, to learn more about internally, is a company called Batricity, that they provide custom energy storage solution using batteries, all those different applications. And then Gilbar has had success with working these in association with EV charging stations, that once again dovetails into the whole carbonization, et cetera, like that, getting rid of fossil fuels. Touching on Aeon, this is a repeat slide, been around since '91. Annual sales, like every vendor, has exploded. Just as there's the number of 634 million. Some of that is attributed to a company that they did acquire. Once again, we in the field like the fact that they're spending money on investing with research and development, capital expenditures, et cetera, like that. Aeon's well known for years and years for these total owner value items. Aeon deals in the applied customized unit from these tonnages, these type of controls. They do have some customizable solutions with a special SPA group for ordering manufacturing. Been very lucky and successful working with that. Just what Aeon has done for cold climate heat pumps is back in the summer, they announced that they're introducing this product. They currently go from 2 to 50 tons. Their performance is laboratory tested and verified down to 0 degrees ambient. The future direction of not just rooftops, but cold climate rooftops, is they're going to increase the capacity, increase or better the lower ambient temperature testing and output, et cetera, like that. And then, like all the manufacturers, they're working on the replacement for 410A with the low GWP refrigerants. What was instrumental in the cold climate heat pump testing was this, innovation testing. There's a picture that I took back in, 2018, before I, busted my ass and fell because I was wearing, dress shoes on a slippery metal floor. Once again, these are, not just for testing, but you guys, as if you want some additional certification, et cetera, like that, all these other items are available. All right, last slide, the last 2 slides here. Just to summarize, cold climate heat pumps are coming. There's, the industry is moving, or the world's moving to less gas heat, more airside heat pump as well as electric heat. You're designing that cold climate heat pump for lower ambient temperatures. For your applications, you're doing a juggling act where you have to consider all these different items for winter operation and leaving air temperatures as a constant volume, et cetera, like that. And then just to summarize, Aeon, we truly believe, is ahead in the cold climate airside heat pump industry. And then, merging with Gilbar, we're very happy about that. Gives us engineering nerds more applied systems to sell. All right. So just to summarize, or here's the last, slide here. Just we do have a survey available. We appreciate if you can fill that out. We do have a PDH available. Just email myself or Gianna. Just as a final summary, we'll send out the resend the PDF of the Prezo. We'll summarize the question and answers. There's this recording was also this presentation was also recorded. So we'll give you the link if you're having trouble sleeping or something like that. You want to watch that at night or something before you go to sleep. Then just, okay, last thing, upcoming webinars, when we have set up is the basics of water source heat pump. I'll work with Climate Master, but I'll be presenting on that. We'll get you the invitation for that. And then just as we traditionally do, try to stay away from the dead of winter in the summer. We'll have a couple more come, April, June, et cetera, like that. Like I said, we try to keep these about 6 weeks apart so we're not overwhelming you with information and requests, and then also giving me some time to do my job as well as to get these put together properly for you guys. All right. So let me escape out of this, Rick, I guess, right? Where'd you go? There we go. Okay. Questions? 2 questions. Okay, if I'm reading the top one correctly. Okay, what is the tonnage and CFM available for packaged rooftop units? Can it be used for lab applications with VAV and 100% outside air systems? So I presume you're asking about the cold climate. As the slide said at the end, the tonnage that we have available currently is up to 50. In terms of CFM, that depends on whether it's a constant volume or a DOAS system. As you know, a DOAS system has much lower CFM per ton criteria. And then can this be used for lab application with VAV? Without a doubt. 100% outside air systems could be, but let's just be careful about our operation, our leaving air temperatures, et cetera, like that. Once again, trying to emphasize we have to be careful or just cognizant of that defrost mode. Once again, there's tricks of helping that out with a adding a wheel, maybe adding a electric heater, et cetera, like that. All right, next is from Jared. Okay, I have seen advertisements from Addison's Frost Shield on their heat pumps, which indicate they are defrost free. They appear to modulate hot gas discharge gas from the compressors to the outdoor coil to prevent frost. It seems that this could also reduce the amount of heat supply to the airstream. But this allows units to stay in heating mode. Is this technology being adopted by other manufacturers as an option to shy away from defrost operation? I have seen the advertisement for Addison's unit. To be honest with you, I have not gone through, like you've said here, where it's probably reducing the amount of heat. I'm not sure if other manufacturers are providing that option or that design. I'm not sure if Addison has patented that. I know that Aeon is not, going that route. They're emphasizing the testing that they can do in their facility, the use of variable speed compressors, and then once again the need for supplemental heat, whether it's electric with preheat or electric reheat, et cetera, like that. Okay, Jacob, there was an answer here. Can you post your email and Gianna's email to request the PDH certificates? My email was on the first slide. You should have received a, we should have seen it on the first slide, but then also too, because you signed up for this, we have your email. We'll we'll send you an email with our contact information, Jacob. And Jacob, you're welcome. Okay, it's 1 o'clock now, so I'm here. Wait a little bit more. Thank you all for coming. Appreciate once again your time. Appreciate many people returning over and over again to listen to me bore you and speak, et cetera, like that. You're welcome, Chad. Okay, question just came in. What are the differences between a digital scroll compressor versus a VFD compressor? In a nutshell, they're both scroll compressors. What the digital scroll is doing is it's using It runs at fixed speed. It's using unloaders where it's turning on and turning off to reduce the capacity. The digital scrolls are typically less expensive than the VFD. You have to just be concerned that the digital scrolls, the sound can become more objectionable where you're, making a noise and then it's off, making a noise, it's off, it's not constant. And then usually the digital scroll can turn down further down to about 10%. The VFD compressors are using, as the name implies, they're using a VFD to slow down the speed of the compressor. You do have to be careful about a few things. One is as that speed slows down, remember that your refrigeration circuit has oil in it. So you have to be careful. There's a lot more safeties and controls associated with the operation of it. There's also a lot of times a oil reclaim system associated with that. And all those make the VFD compressor more expensive than the digital scroll. Any other things about the digital scroll versus the VFD or anything I didn't miss? Went over cost, operation, capacity control, maintenance, obviously, because the VFD compressor has the VFD, there's more maintenance associated with that, more moving parts, there's more electronics versus the digital scroll. Yeah, exactly. Yeah, just realize that the VFD can overspeed, so that's what they're using for the cold climate. The digital scroll cannot overspeed. The max is 100% capacity. That's 60 hertz. All righty, 103, I'll stay on for another couple minutes. Once again, thank you all for attending. We'll send out a summary with all the questions and answers. If you do have other questions, feel free to email me or your HCNI salesperson. We'll get back to you. Signed off. Jerk. Jerk. Signed off. Jerk. There I am. Damn, look at that hair. Should have put some goop in it. Oof. All right, everybody, 105. Oh, one more question came through. Sorry. Can you discuss AHRI certification? I might have to, Rob, I might have to table that one. From what I understand is for packaged rooftop units, for the cooling side of it, there's much more information regarding coefficient of full load efficiency and part load efficiency. There are certain operating conditions that have to be met. with the Airside heat pump, I believe the ASHP certifications are only currently at 47 degrees ambient as well as 17. I'm not sure if they are down to 0 yet or minus 20. The one thing I will say about the ASHP certifications, that you see in the standards and stuff like that, is that to me it doesn't really indicate your operating your operating conditions. B, if I remember, your airflow is traditionally lower than like 400 CFM per ton. In addition, the external static pressure is traditionally very low, like a quarter inch or something, that half inch that to me you would never see on a rooftop unit. And then the other thing that I shouldn't say screws it up, but just throws a monkey wrench into it, is that today's units were almost always selecting hot gas reheat for dehumidification control. And once you do that in your selection, that kind of quashes, the ARI certification does not cover cooling only units with hot gas reheat, et cetera, like that. So as general, okay, thanks. Okay, all right, thanks, Rob. Yeah, maybe if you can further clarify, like, okay, you're concerned about AirTry certification with the ambient heat pumps or cooling only, et cetera, like that. That could help me focus or research, what's the best answer or get you a correct answer to that. All right. Thanks. All righty. Okay, everybody. Thanks once again. 108 here. If you do have any additional questions, please feel free to, like I said, email me or email your salesperson, HCNI salesperson / Old Gilbar salesperson, and we'll get back to you. All right. Okay. Thanks once again. Have a good week, everybody. See you soon.